Hello everyone, this is Sahidul Islam. I am a PhD student at the University of Texas at San Antonio. Today I am going to present our research paper, Environmental Adaptive Neural Network Models for Low Power Energy Harvesting System. And this is a joint work from UTSA, University of Connecticut, and Lehigh University. So first we will talk about background and motivation. Here we will also discuss adaptive deep neural network and its importance for energy harvesting device and how to achieve such adaptivity. Next we will talk about shared weight concept. Here we discuss how to share weights among multiple deep neural network models. And we further discuss how to find shared weight models with using AutoML search. Finally, we will provide on-device architecture where we show how do we extract and run an individual model from the shared weight source. And lastly, we will show the evaluation results. Let's start with background and motivation. So, what is energy harvesting devices? Energy harvesting devices runs without battery power. Instead, its energy source are environment such as solar, thermal, or wind. Therefore, this device has very small resources and the computations inside those devices are intermittent. So these are some examples where this device can be useful to track animal or wildlife. This device can also be useful in monitoring environment and human body. However, energy harvesting is not a free lunch. This figure shows four different traces collected from different energy harvesting sources such as RF, PGO, thermal, and solar. From this figure, we can see that no matter what method it is, they are usually weak and intermittent. Implementing AI algorithms such as deep neural network in energy harvesting device is a challenging task because of the small resource and intermittent behavior of those devices. However, DNN is more mature now than ever, and it is important to achieve on-device AI because executing DNN on cloud needs a lot of communications between device and the cloud server. Instead, if we can run DNN inference on device, we can reduce communication cost and get real-time decision. And on the other hand, on-device AI also enhance privacy and security for the user. To deploy deep neural network in resource-constant device, researchers developed several compression and pruning techniques. One of the methods is kernel pattern pruning, which can be applied in convolutional neural network. So pruning is a technique to remove redundant information from weight. In pattern-based pruning, based on a particular pattern, reinformations are removed. For example, this is a weights of a convolutional neural network which consists of several filters, and every filter consists of several kernel. Now, if we take a single kernel and apply 3 anti-pattern pruning, so we can have a different shapes. This is one shape, and the shape can be like this or like this. And if we apply 4 entry pattern, the shape can be like this or this. And if we apply 6 entry pattern, the shape can be like different. So the important part is this is the pruned weight, and these are the remaining non-zero weight of a kernel. Let's consider situations where DNN inference took place in an energy harvesting system. You can see depending on the power availability, the inference time and energy can vary. In stable power, the inference is smallest. But when the power is intermittent, depending on the power availability, the latency changes. In high power availability, inference takes small number of power cycle and the overhead is also small. But when the power availability reduces, you can see the number of power cycle and the overhead also increases. For example, you can see in high power availability, inference takes 10 seconds and energy consumption is 20 millijoule, but in medium availability it's 20 seconds and 25 millijoule, and in low power availability it's 30 seconds and 30 millijoule. Since the latency becomes too high in low power, can we do something? One solution can be we can run a lightweight model when power availability is low. This will allow us to maintain latency and energy requirement while slightly reducing the accuracy. But it requires multiple deep neural network models to deploy, where each model will be executed in different power mode. Then the question comes, how do we deploy multiple deep neural network models in resource constant devices? The answer is weight sharing. Now we will discuss the details of weight sharing concept. This is a 3x3 kernel and we are going to apply pattern pruning on it. Let's apply a 5-entry pattern. After applying the pattern pruning, the remaining weights of the kernel will be like this. Since 4 elements are removed from the kernel, we are calling it as a small pruning. Now, if we apply 4-entry pattern in the same kernel, then the remaining weights would be like this. Since 5 elements are removed, we are calling it as medium pruning. Again, if we apply 3-entry pattern in the same kernel, the remaining weights would be like this. Since 6 elements are removed from the kernel, we can call it high pruning. Now, if we look at the remaining weights after several levels of pruning, we can see that some information can be shared. In this research, we will apply several levels of pruning to generate different size of model, which will run in different energy or power availability. Our goal is to maximize the shared weight among these models so that multiple models can fit in resource constant energy harvesting device, and the weight can be reused while lowering the memory footprint. Next, we will discuss AutoML search. This technique will allow us to find such shared weight model. This is the overview of the AutoML search framework. The input of this framework is hardware resources like latency and accuracy constraints, as well as a backbone DNN model. The core of this framework consists of reinforcement learning based algorithm, which has several components. Search space consists of several pattern pruning samples. Hardware performance predictor roughly predicts the performance. Shared weight training architecture train the compressed models. And there is also an RNN based controller which calculates rewards for a particular pattern set. And finally, the output is generated, which has 3 shared weight compressed models. Now we will discuss shared weight training process. We firstly train a model with highest pruning. Then we keep the unpruned weight unchanged and continue training to fill the pruned weight with real values so that we get the medium pruned model. Following the same way, we continue train on medium pruned model and finally achieve the small pruned model. Thus, we achieve low, medium and highly pruned model. Next, we will discuss the on-device architecture of the shared weight model. After AutoML search, we achieve multiple shared weight models. Here, blue patterns represent highly pruned or high sparsity model, yellow pattern represent medium pruned or medium sparsity model, and finally the green color represents small pruned or small sparsity model. Next, we compress them by eliminating pruned information and represent these with 1D array. Here the location index represents the address of the associated applied patterns. Applied patterns are represented with bit matrix. So during inference, a particular model needs extraction based on the availability of the power. We will discuss the model extraction and computation process in the next slides. Let's talk about the model extraction process. So SWM is the compressed shared source which is derived from the 3 sparsity patterns such as high, medium and small. And there is a pointer which will point to the first element of the SWM. Let's say we will extract the small model which is represented by the blue pattern, and therefore the blue pattern is our desired model pattern. And the yellow and green patterns are the other model patterns. Now we will iterate through the desired model pattern first. So if we find a 0 in the desired model pattern, then we will look for the other model pattern with the same index. And if it's also 0, we will not take the source to the output and we will not change the pointer. So this state is called do nothing state. Now we will iterate to the next element. If we find a 1 in the pattern, we will not look for the other patterns. We just immediately move the pointer and move the source to the output location. So this step is called the take step, and in this step we will take the source and move the pointer. We will continue iteration. We will move to the next element, and which is 1. Since this is 1, we will not look for the other model pattern information, so we immediately move the source pointer to the next location and move the source to the output location. Now we move to the next element, and this element has a value of 0. Since we have already said when we find a 0 in the desired pattern, we will look for the other model pattern values, and this time the other model pattern value has a 1. If we find any 1 value in any other model patterns, then what we will do, we will move the pointer, but what we will not do is we will not take the source pointer to the output location. So that's why this step is called the skip step. Now we move to the next. This is also 0, and we will look for the other models. Here is a 1, so this falls into the skip state. We will move the pointer, but we will not take anything. So we will continue doing this. This falls also into the take steps. And after finishing the iteration through the desired pattern, the output consists of the condensed weight. So after the extraction process, we have the condensed weight. Condensed weight also have location index. By using location index, we find the applied patterns, and we will use this applied pattern to the input window and find the pattern wise input and move it to the ALU. And we also move the condensed weight to the ALU, and we will perform multiply and accumulation operation using low energy accelerator or CPU. And finally the output is written to the output location, and this is how the convolution operation is done. And now we will talk about the experiment and results. For the hardware setup, we use Texas Instruments MSP430 FR594 device, which has a low energy accelerator, and we also use functional generator. And for the IDE, we use Code Composer Studio. It also has the energy trace technology to measure the energy. And we use 3 deep neural network models and dataset. So first one is digit recognition for MNIST, a human activity recognition for HAR, Google keyword recognition for OKG dataset. This is the result of the DNN models with and without reinforcement learning based AutoML search. Here SW train shows the result that does not employ reinforcement learning based search. On the other hand, Eve implemented the reinforcement learning based AutoML search algorithm. Here we have shown 4 DNN models, LeNet5, HRNet, OKGNet, and SqueezeNet. Here every DNN model consists of 3 submodels, which are basically 3 different sparsity models discussed in previous section. Here M1 is the high, M2 is the medium, and M3 is the low sparsity model. We can see that Eve improved the accuracy for the MNIST model ranges from 0.01% to 0.89%, and latency is also improved up to 0.07 second. For HER model, accuracy can be improved up to 2.21% and latency can be improved up to 0.01 second. And for the OKG model, accuracy can be improved up to 0.6%. And for the SqueezeNet model, accuracy can be improved up to 3.33% and latency is 0.1 second. Here is the result of on-device latency and energy consumption. The HW train and Eve is our framework, while N-prune baseline is the naive procedure where three models are not pruned and kept in secondary memory. And during inference, a particular model needs to load it into the primary memory. On the other hand, the Y-prune baseline has the pruned model, but they do not share weight. On the other hand, the SW train and Eve has shared weight and kept in primary memory. We can see that our proposed baseline, the SW train Eve, has very low latency and power consumption in terms of other baselines. One thing to note that we do not show the SqueezeNet data since it requires secondary memory to load a single model. Now here is the result of different model when the power is intermittent. Here the gray box represents the power off time and the blue box represents the inference time. From three figures we observe that when the harvesting power is low, the execution time is increased. Therefore, in order to meet the quality of service, the energy harvesting device needs to automatically switch to the low accuracy model, which takes much less time. In conclusion, in this paper we propose IF, which is a novel pattern pruning based framework that produces and implement multiple hardware friendly models with shared weights. IF also consists of AutoML based co-exploration framework which searches the desired multiple models with shared weights. We also propose on-device implementation architecture that compress the shared weight kernels and extract the kernels for the corresponding individual model according to the energy levels. So thank you everyone. If you have any question, feel free to contact me. Goodbye.